So we saw back in chapter 3, I think it was, that a chemical change, right, is defined as one in which there's a change in the identity of the substance. So we start off with something and it changes into something brand new. That's a chemical change. We represent chemical changes or chemical reactions by using chemical equations. And we'll take a look at the chemical equation in a second. In lab today, and in lab on Monday, you saw one or maybe multiple things that told you a chemical reaction happened. So I'm going to pick on the people that had lab on Monday. What were some things that you observed that told you a chemical change or a chemical reaction happened? What was one of the things that you saw in lab on Monday? Monday, people. So did you see a change in color at all?
Yeah.
So color change. So a color change was indicative of a chemical reaction. Okay. Anything else? Bubbles. Okay. So bubbles. So if you see bubbles, what does that tell you is being produced? A gas. Temperature change. So you were able to feel temperature. So did the thing get hot or cold? You got warmer. Okay. So temperature change. Anything else that you saw? Monday, people? There was. Sorry, what was that? Noise? You saw noise or you heard noise? Okay, so that's the end result of the change. Okay, so hang on to that thought for a second. Any other things that you? Odor? Or smell. So again, that's not something you would see, but you would smell. That's also an observation, right? Just like the sound that you heard. So an odor. That's it. Let me respell that. An odor produced, right? So there wasn't an odor at the beginning. You mixed a couple things together, and then whatever you made ended up having a smell that wasn't there at the start. One more thing that you saw. Light being produced, okay. Yes, but one of the reactions that you did, you mixed two things together, and then did you remember it turning cloudy? Yes, so that cloudiness tells you that you produced a solid. Right, so all of those are indications that a chemical change or a chemical reaction has occurred. And as you saw on Monday, and as you'll see today, you may see a couple of them, or sometimes you'll just see only one of them, or observe one of them. So a chemical equation then is what we use to represent these chemical changes, right? So you can think of a chemical equation as sort of a chemical sentence. So for example, we can say that two molecules of hydrogen gas react with one molecule of oxygen gas to produce two molecules of liquid water. Right? That's a regular run-of-the-mill sentence. A grammatical sentence. We can take that and convert it into a chemical sentence or a chemical equation that tells us the exact same information without losing anything. But it's a lot more concise. So for example, then we can say two molecules of hydrogen gas. Now remember, hydrogen exists in what form? H or H2? H2. It's one of the diatomics. It's a gas. We use G for gas. React with 1 molecule of oxygen gas. What's the formula for oxygen gas? That's also O2, to produce 2 molecules of water, which we know as H2O, and it's a liquid. Okay? This thing in red is a chemical equation. It's a chemical sentence where we take those 3 lines and we put it in a form that is way more concise. We haven't lost any of the info. Right? We've faithfully translated that into an efficient form. And we're going to be dealing from this point onwards with these chemical equations. Right? And the basic layout is going to be the same throughout this class at least. So when you write a chemical equation, when you see one, the layout, like I mentioned, is going to be the same. We're going to have an arrow in the middle, and that arrow you can think of as meaning produces. So the water and the oxygen on the left, the hydrogen and the oxygen on the left side of the arrow, these are called reactants. So the reactants react together to produce the stuff on the right side, which we call products. Right? That's the basic general layout for every single chemical equation. Reactants on the left react together to produce the products on the right side. You will notice that we use a couple symbols in here to mean certain things. So for instance, the most common symbols you'll see used in chemical equations, right? G in parentheses means that thing is that's a gas. We use L, small l, for liquid. S means it's a solid. And then there's a fourth one that we're going to see, AQ. This stands for aqueous, which simply means that whatever that thing is just dissolved in water. Right? So those are the 4 physical states and state symbols. We call these state symbols that we're going to observe in a chemical, we're going to see in a chemical equation. Right? So chemical equations represent chemical reactions or chemical changes. Another symbol that you'll see is sometimes you'll see a triangle. Right? And it'll be placed either above or below the arrow. Right? You don't always see it, but when you do see it, that triangle in the right above or below the arrow, this means heat. All right, so chemical equations represent chemical changes. We have reactants on the left side that react together to produce the products on the right side. All right, so now we know how to represent, how to interpret these chemical equations. We need to address one very, very important thing when it comes to equations, which is we cannot violate one of the more important laws in chemistry and science as a whole, which is the law of conservation of matter. So when we start looking at equations, we're going to have to make sure that they are balanced, which simply means that the number and type of atoms on both sides of the equation are equal to each other. All right, and then this is just another way of stating the law of conservation of matter. Right? You cannot create or destroy things. You can simply convert them from one form to another. So the total number of a particular type of atom that you start with should be the same number of atoms of that type that you end with. So if you start with 10 oxygen atoms, you should end up with 10 oxygen atoms.
With the H2O, how went from 2H2 plus O2 to 2H2O?
Right.
I'm confused as how, because like H2 and O2, I don't know that's how water is, but how does H2 keep its subscript and then O2 loses its?
Yeah, so we'll address that here in a second. So the balanced equation, right, we need to make sure that we work with and we use balanced equations so we don't violate the law of conservation of matter. So we'll go back to that equation here in a second. Let's do it right now, actually. So we saw, well, before we put the numbers in, let's say we had our hydrogen reacting with oxygen to make H2O. All right, I'm omitting the state symbols right now just for simplicity's sake. So the way that you want to approach your equations when you have to balance them, right, is to just make a list of the atoms that you have on both sides of the equation. So on the left side, on the reactant side here, I have a bunch of H's and I have O's on the left side.
Do you not need the big 2 in front of H?
We're going to get to that in a second. We'll show you why we have that. And then on the right side, we should also have H's and O's, right? Because you can't destroy them. So we should have H's and O's on the right side. So we list the atoms that we have. And then we're just counting. How many H's do we have on the left? 2. Look at the subscript. How many O's on the left side? 2. How many H's on the right? 2. Right? The subscript in H2O there is 2. And how many O's are on the right side? 1. Right, remember, when you don't see a subscript, 1 is understood to be here. So all we're trying to do now is to make sure that we have the same number of H's on the left as we do on the right. And we have the same number of O's on the left as we do on the right side. That's what following the law of conservation of matter is. We cannot create or destroy stuff. We have to start with the same number and types of atoms that we end with. So are the H's balanced right now?
Yes.
Do we have the same number of H's on both sides? Yes. Are the O's balanced? Do we have the same number of O's on the left or the right? No, we do not. Right? We have 2 O's here, and we only have 1 O on that side. So the way that you balance an equation, right, there's only one way to balance an equation, and that is you have to change the number of that substance that you're lacking. So for instance, if I'm lacking my oxygen, I can't just say I can change my subscript here, right? You're not allowed to change a subscript. That's forbidden. So you cannot change subscript. So I can't simply say put a 2 right after the O. Can't do that. So how can I make 2 O's on the right side? Can I put a 2 right in the middle, like so? You think that makes sense? No, right? That's a violation of all sorts of things. You can't just stick a number in the middle of the chemical formula. The only thing you can do is to put a number in front of the entire chemical formula. And we call these coefficients that we're going to place in front of each of the formulas in our equation. So if I want to make 2 O's, I want to have 2 O's on the right side, the only thing I can do is to have 2 of the water molecules. Right, so I can change my coefficient now to 2. Coefficient is just a big fancy word that means a small whole number. or a small integer that we're using. So if I put a 2 in front of that H2O, I change now everything that comes after that 2. So now I have to go back and rebalance. How many H's do I have on the right side now? Right, everything that comes after the 2 gets multiplied by the 2. So now I have 2 times 2, so I have 4 H's on the right side. How many O's do I have on the right side now? I have 2, right? Because I put the 2 in there to balance my oxygen. So I have 2 times 1 O gives me 2. So my O's are good, but now I put my H's out of balance. Now I need to make 4 H's on the left. So what do I need in front of the H2? You need a 2. And that gives me 4 H's. In front of the O2, there isn't a coefficient. What is understood to be there? 1, right? So when you don't see the coefficient, you can put the 1 in if you want. Do not put 0. Right? 0 means there's nothing there. Right? So that's why when you write the equation for the formation of water, we said 2 molecules of the hydrogen react with 1 molecule of O2 to make the 2 molecules of water. Right? That is our balanced equation. It is extremely important that when you deal with chemical equations, that before you start doing any sort of calculation, that you ensure that it is balanced. Okay, if it's not, I guarantee you that all the stuff you do afterwards is going to be wrong. Okay, let's take a look at a couple other examples. Where did my thing go? Okay, so let's say that I had this equation. So CH4 is methane reacting with oxygen to make CO2, carbon dioxide, and water. Okay, and as you're going through this, right, I would recommend that you just put a line in front of each of the formulas. That way you know the only place where you can stick these coefficients in, right, which has to be at the front. And then we go through the process. We list all the atoms that we have on both sides, and we should have the same types of atoms on both sides of the equation. So on the left side we have carbon, we have H, we have O. And on the right side we have carbon, we have H, and we have O. And we're counting. How many carbons on the left? How many H's on the left? How many O's on the left? What about on the right side? How many carbons do we have? 1. How many H's? 2. And how many oxygens? Okay, so now, right on the right side, you'll notice that your oxygen is actually found in 2 places, right? And that's a really good or maybe bad place where you can forget about the oxygen. So please keep in mind, right, that you may run into an instance where a particular atom is split between 2 different places. So you have 2 O's here, and we have the 1 from the water. So we have a total of 3 oxygens. So this leads into your first strategy that I would suggest to you when it comes to balancing equations. You have a choice now, right? When you look at your equation, is anything balanced so far? The carbon is, but the H's and the O's are not. So which one do you want to balance first, the H or the O? So one strategy that you may want to use as you go through this process is if you notice that there's an atom that is split between 2 different places, like the oxygen is, leave that till the end and balance everything else first. Right? It's not that you're not going to get the right answer, it's just going to take you longer to get there. So that's my first suggestion to you. If you identify an atom that is found in different places, save that one to the end, and hopefully, most likely, when you balance the other ones, that one ends up being just a one-step process. So let's balance the hydrogens. So we have 4 H's on the left, we need 4 H's on the right. So what do I need? How would I balance my H's on the right side? A 2 in front of the H2O. Okay, so then when you put that in front of the H2O now, we've changed our hydrogens to 4, right? But we've also messed up our O's. Now how many O's do we have on the right side? So how many O's on the right? Okay, I'm hearing 3, 4, 5, somebody say 8. There's 4, right? So 2 from the CO2 and then 2 from the H2O. So 4 O's on the right side. And now to balance my O's on the left, all I would need would be a 2 in front of the O2, and that gives me 4. All right, carbons are good, we didn't mess with those, and they still are balanced. That's your balanced equation. 1 methane with 2 oxygens to make 1 CO2 and 2 H2Os. Really what balancing equations comes down to is just trial and error, right? You stick your numbers in where you think they belong, and if it doesn't work, try something else. But it's not just, haphazard, right? There's a little system to it, like we kind of went through here. Right? So little strategies you can use to help you balance equations a little bit more efficiently. Okay. Let's take a look now at another instance or other instances where we do run into equations that may look ultra complicated, but we can make it a lot easier to work with. All right, so here we have an equation where we're dealing with sodium. Well, let me ask you, what's the name of this compound? You had to name this a couple weeks ago. Sodium phosphate, magnesium chloride, magnesium phosphate, sodium chloride. Right, so those are all ionic compounds, and then a couple of these things may look familiar to you. Right, the PO4, that's a polyatomic ion. That's one of the several that we looked at in lab. All right, so when you are faced with this equations that contain polyatomic ions, right, you may be tempted to go ahead and separate all of the atoms into themselves. So for instance, you may want to think, well, there's sodium, there's P, there's phosphorus, there's oxygen, etc. One strategy that you can use to make the balancing a lot easier is to balance the polyatomic ion as an entity. In other words, don't break the polyatomic ion into its atoms. Okay, so what do I mean by that? Well, we'll go through and list. So we have sodium on the left side. All right, and then you have to recognize that the PO4 is the phosphate ion, the polyatomic ion. And we're going to treat it as PO4. We're not going to split it. So we're going to balance it as a collection, PO4. And then we have magnesium, and then we have chlorine on the left side. We should have those same things on the right in order for this to work. Right? So we have our sodium on the right, we have our phosphate, we have our magnesium, and then we have our chlorine. How many sodiums are on the left? We look at the subscript, right? 3 sodiums. How many phosphates, how many PO4s are on the left side? 1. Right? If it helps you, what you can do is just put a pair of parentheses around your polyatomic ion, like so. Right? And you can see there's just 1 of them. How many magnesiums on the left? 1. How many Cl's on the left? 2. Right? We do the same thing now on the right side. How many Mg's on the right? Okay, 3 Mg's on the right. How many phosphates on the right side? PO4s? Phosphates, the PO4s. Two. There are two, right? The subscript tells you how many phosphates you have. You have two of them. And then we have one sodium and one Cl. All right, so again here you have a choice of what to balance. Nothing looks like it's balanced. And so it doesn't really matter where you start, like which one you start with, you'll still end up with the same answer, right? But as you get more and more practice with this, you'll figure out that, well, if you start with one thing, it gets you to the answer a lot quicker than if you start with another thing. All right, and that only comes with practice. So, well, if I start balancing my equation now, I can look at my magnesiums and I can see, well, let's see, I have 3 magnesiums on the right side, so I want to balance my magnesium on the left. So what would I need? I need 3 of them, right? So right now I have 1, so I would need what in front? You would need 3 in front of it, because the 3 multiplies everything that comes after it. Right? It's not additive, it's multiplying. So we'll put a 3 in front of the MgCl2. So now we have 3 Mgs, and how many Cls do we have now? Chlorines. 6. So let's deal with the chlorines right away. 6 chlorines on the left. How do we make 6 chlorines on the right side? You put a 6 in front of the thing with the chlorine, right? Which is here. So now you've made 6 Cls. Now you've changed your sodiums to 6. Well, let's address the sodium. We have 6 sodiums on the right side. We need 6 sodiums on the left. So I'll put a 2 in front of the sodium phosphate. So 3 times that 2 gives me 6 sodiums. And now how many phosphates do I have on the left side? Now I have 2 of the phosphates. Right? So the phosphates automatically balance themselves in this equation. Okay? You could have started anywhere. We started with the magnesium because I know that if you start with the magnesium, you get there quicker, right? But you could have started anywhere else. You may have spent a couple extra minutes, but you would get to the same answer. All right? Similarly, right, my suggestion to you is that you balance your polyatomics and you keep them together. Right? If you wanted to, you can separate them into individual atoms. It'll take you a lot longer, though, to get to the answer. Right, so that's your second strategy for balancing equation.